We started this slide set last time, but we didn't finish it on the column design. And we're going to have more than one slide set for column design. The first slide set here is going to be mainly on the design of tight column, which means this type of columns. Second one is going to be the spiral column. So the first one, again, for tight columns, we said that provided the ties is going to increase the confinement of the concrete. Confinement means that when you provide this containment for the concrete with the ties, and then you start with pressure, it wants to open up. But what's going to stop it is going to be all of these ties. So this ties here is going to improve the properties, includes the strength and the ultimate strain of the concrete. And we're going to see a diagram for this in the next slide set. So having the ties is going to help to reduce the buckling length for the vertical rebars exposed to compression, and also is going to help to increase the properties of the concrete. So how many reasons for the ties? Can someone remind me here again? If you can repeat this, please. Why do we have ties for columns?
To make sure column buckling doesn't occur.
Column buckling or the rebar buckling?
Or rebar buckling.
Okay, rebar, not the column. Okay, that is the first one. How about the second one? Anyone remember anything that I've just said? Provides what to the concrete?
Strength.
Reinforcement, just
Confinement.
Confinement.
Would you please remember this term here? Confinement. So I'm going to say this ties here, they provide confinement. So I'm going to put here confinement. And this confinement that you provide to the concrete is going to enhance the concrete properties. So the reason that we put this ties, again, for two reasons. And actually, this gave you a very good question for one of the quizzes or exam. This is why I'm just repeating it. So number one, provide the restraint to the vertical rebars and to prevent their buckling or to reduce their buckling length. Number two, provide confinement to the concrete and enhance the concrete properties, such as the strength and the strain. Which is strength? Maximum strength. Which is strain? Ultimate strain. We went through this, and here's, if you look at this one here, because you have more confinement in the spiral reinforcing, so in the spiral column, generally speaking, you have more confinement. This is the reason that the concrete performance here, the concrete column performance, is going to be superior in case of a spiral column versus tight column. Would you like to see here the difference between the ties and a tight column and a spiral column? Look at the amount of reinforcement that you have here for the spiral versus this. So here is going to be higher. Also, we discussed this issue of the fee factor. We said that the code recognizes this issue. So when you go to the code, it doesn't say because you have more confinement, but instead they give you a different fee factor when you have a spiral column versus tight column. When you have columns, it's going to be mainly compression control, which means we're going to be in this region here. So fee factor for tight columns is going to be 0.65, for spiral columns is going to be 0.75. Say that you have an equation. This equation for the axial column capacity. So VPN is going to be the axial capacity. Is equal to 0.8. We said this 0.8 is a reduction for the total difference to account for some small eccentricity. So this axial component here, or this axial strength, considers that you're going to have some small eccentricity and you can ignore it. Ignore what? Ignore the eccentricity. So generally speaking, eccentricity is going to be causing additional moment that goes with the axial column load. So when you have any vertical load, I'm going to go back here a few slides. I marked this before. I said if you have this axial column load, and you have some eccentricity, it means that you're going to have this axial load plus additional moment is going to be coming this way. It's going to be clockwise in this case. It means that your column here is exposed to axial load and moment. But as long as this eccentricity, I'm going to call it a small eccentricity, I don't really need to check the moment applied on the top of the column. I will just take the axial column load capacity. Meaning, again, this equation here. This equation does not consider the effect of moment applied to the column with the axial load. But this equation here says if you have a small eccentricity, you should be able to ignore it, which means ignore the applied moment on the column, as long as eccentricity is going to be called the small eccentricity. But we don't have a definition yet for the small eccentricity. Very soon, we're going to have a definition for it. So the column strength is going to be equal to phi, and your phi factor is going to be 0.65 for tight columns, multiplied by 0.85 F prime C AG minus AST, which means the net concrete cross-section area. So this box here, or this term, is going to represent here, will represent the concrete compression strength. And this term here is going to represent the steel compression strength. We just consider the steel to be yielding. The equation is very simple, as you see here. There is no strain calculation to prove the phi factor or to justify the yielding point. You just use it as is. The amount of steel ratio goes from minimum of 1% of the cross-section area of the column to 8%. It says here from 0.01 to 0.08 of A sub G. You need to have at least 4 rebars in a column because each corner needs to have 1 rebar. Okay, yeah, you understand that. We went through this. Also, we discussed this maximum spacing of 6 inches. So this spacing here needs to be less than or equal to 6 inches. Okay. Look at the tie spacing. Tie spacing, we said, according to the code, I have 3 items here that I need to justify. To satisfy these 3 requirements, it says number 1 is going to be 48 times the tie bar diameter. And it's going to be also 16 times the longitudinal bar diameter, this vertical bar diameter. And also it's going to be equal to the least column dimension. So, okay. If my column, as just an example, has number 4 ties, so the tie is going to be number 4, just like this tie. And the vertical bars is going to be number 8, like 1 inch. How can I apply the 3 conditions or 3 minimum values? Actually, call this going to be the maximum bar spacing or the tie spacing. So it's going to be the maximum tie spacing, if you like. Look here for the tie size. It's going to be number 4. Number 4 meaning half an inch times 48 is going to be 24 inch. How is that? 48 times half an inch, 24 inch for the spacing between 2 ties. If you look here at the second condition, it says 16 times the number 8. Number 8 meaning 1 inch. So it's going to be 16 times 1. It's going to be 16 inch. Column size 12 by 24 cross section. So I'm going to say the least column dimension is going to be 12 inches. This is all good, but once you come here to California, they said, well, for this column, we understand this is going to be gravity column, but we have also some seismic requirements on the gravity column. Because this column here is going to be moving right and left with the entire building. So it's going to be exposed to drift. Drift means this lateral displacement. So in California, it says maximum spacing here is going to be 6 inches. Just to satisfy the seismic requirements for the gravity columns. So, okay, good. Doesn't look that tough. Also, we have some calculations for this tie reinforcement. We have an equation for it, but we're not going to cover it today. Okay, good. Now, which number should I pick? I have 24-inch, 16-inch, 12-inch, and in California it says here 6-inch. So what's going to be the maximum spacing? Should I go to 24 inches? If I go here to 24-inch and look at this, it says 6-inch max. So you cannot really use 24-inch, you cannot use 16, you cannot use 12 in California. You need to use 6 inches. So as long as you work in California, you're going to have a maximum of 6 inches. In this example, it says find the maximum design axial load for the tied column. So here's the tied column. The size of it is as given. It says 16-inch by 16-inch. And then it says check the ties. Assume short column, which means no buckling effect of the column. We're just going to be ignoring it here. So our business is going to be only with short columns. Concrete strength 4,000 psi, and yield strength for the steel is going to be 60,000 psi for both longitudinal and steel ties. Okay. About Vertica Rebars, it says that you will have here 8 number 9. Let's see here 8 number 9. And the spacing, it says 16-inch for the ties. Number 3 ties at 16-inch. It doesn't say that this needs to be built in California. It is taken from your textbook. Your textbook is very generic. It doesn't address California construction. So I'm going to say in this case, I don't really need to check this out, but I need to check the 3 items. Okay. Let's hear the equation. I need to check first is going to be the amount of rebars, vertical rebars that I put in there. Code says you're going to have a steel ratio that goes from 1% to 8%. I'm going to go back here a couple of slides. Just look at it and confirm it. It says here not less than 1% or more than 8%. So I have a range here for the vertical steel ratio for the vertical rebars. So number 1 check, I'm going to be checking here the 1% and 8% and see if our steel ratio is going to be within this range. All right, I have 8 number 9 and the column is 16 by 16. Moving here to solution. This here what we call the steel ratio. So this one is the steel ratio. Vertical steel ratio, if you like. It's going to be equal to total cross-sectional area of the vertical rebars divided by the cross-section area for the concrete column. I have 8 number 9. For 1 number 9, cross-section area for 1 number 9 is 1 square inch. That's why AST is going to be 8 times 1, 8 square inches. The column size cross-section area is 16 by 16. So the ratio, if you do the analysis, is going to be like 3%, 3.1%. 0.03 meaning 3.1%. This is good. Why? Because we are in between or we are within the range. Our range is going to be 0.01 to 0.08, from 1% to 8%. So this is good. The choice of having 8 number 9, I'm going to go back here one slide. 8 number 9 in a column of 16 by 16 is okay. Nothing is wrong with this. How about the axial column capacity? Let's say axial column capacity. I guess I need to use this equation from the code. This is a tight column. This is non-spiral column. Just copy this equation again from the code. 0.8 is just a constant. This is to account for small eccentricity. Now here's the question. Did it say any small eccentricity here or big eccentricity? I'm going to say no. Any indication on any moment applied on the column? I'm going to say no. So you have no moment applied on the column, not mentioned here. There's not about eccentricity. So I'm going to assume that this is going to be concentric column. Concentric means that the vertical load is going to be right in the middle. Eccentric is going to be shifted. Concentric is going to be right in the middle of the column. The phi factor, as we said, for tight columns is going to be 0.65. Then you have 0.85, 0.85. What is that? I'm going to say this is going to be for the concrete strength, for concrete contribution. And this section here is going to be for the steel strength. Right? So fine. So I have here 0.85 times 4 KSI for the strength of the concrete. How about A sub G? This one is, which one is this? Which one is 256? This give you like 16 by 16. It's going to be equal to 256 square inches. Subtracting 8. 8 is going to be the cross-section area of the steel, like this one, 8 times 1. So now I'm done with the concrete strength. So, okay, this is good. This is now the concrete strength contribution. How about for the steel? The steel is going to be 8 square inches multiplied by 60 KSI. Run your analysis, and with that, PPN is going to be equal to 688 kips. This column should be able to support up to 688 kips of an axial load with some small eccentricity. If nothing is mentioned here about eccentricity, it means we have an assumption that we have with small eccentricity. Any questions? Yes? No? All right, now let's check the ties. Tie spacing, my understanding here is again the column. I'm going to go back a couple of slides. Number 3 ties at 16 inch. And the column size 16 by 16. Okay. The bar is number 9. 1 1/8 of an inch. The code says you have here 3 limits, plus a 4th one if it says in the problem that you're in California. Now it doesn't say, so I'm going to treat it as this is just a standard column in any other state. It says here for item number A, this is going to be the first item that you need to check. It's going to be 48 times the bar diameter. 48 times, now it says number 3. What does it mean by number 3 for diameter? You say number 3 means 3/8 of an inch. So you say 48 times 3/8 of an inch is going to be equal to 18 inch for the spacing. So the first condition here, it says your maximum spacing is going to be 18 inches. Okay. Second one, it says 16 times the vertical bar diameter, longitudinal bar diameter. I have here number 9. Number 9 means roughly 1 1/8 of an inch times 16. It says also 18 inch. Same as this one. And then says also the least column dimension. The column 16 by 16. So I have square column, and the column dimension here is 16 inches. Now, which one is the smallest of all of these? I'm going to say this one here controls the spacing, this dimension here, 16 inch. So 16 inches is going to be the limit. Now, what have you provided in this problem? I'm going to say you have number 3 at 16. So this is good. I have no problem at all. So this spacing and the tie is good. I have no problem with the ties. I have no problem with the vertical rebars. Now I need to check here the spacing between 2 vertical rebars, which is this check here. So I'm going to take you back a few slides to show you which one I'm talking about. Talking about this spacing here. How can you do this? We have this case, exactly this case. The clear spacing, it needs to be less than 6 inches. So okay, 6 inches. How can I do this? How can I do the analysis? If you have the total length of the column, like 16 inch, you subtract the cover, you subtract the tie size, you subtract the rebar size itself, and then you divide at the end by 2. So okay, yeah, I guess I should be able to do this. Our problem here, I have 16 inch. I have 1/2 inch of the cover, clear cover. I have number 3 for the ties. So I said, okay, let me check. Can I have here 16 inch as a column dimension? So we can say this is here the column size, the column. It says here 2 times 1.5. What is that? Can someone help me with this? What is that section? What is that term?
That's for the cover.
Yeah, 2 times the cover. Let me just turn this on. Excuse me for that. So here's the cover, 2 times 1.5. Now also I have this 2 times 3/8 of an inch. Can someone help me with this? What is that for?
It's for the diameter of the ties.
2 times the tie diameter. All right, so this is going to be 2 times the tie diameter. I'm wondering about this 3 times. What is that?
It's 3 times the diameter of the reinforcing scale.
Yeah, which reinforcement? For the vertical bars, right?
Yeah.
So I have 3 bars. This is true. So almost 1 1/8 of an inch. So let me go back here, just check this out. So what I have done here, I have taken the total width, subtracting 1.5 inch from each side, subtracting the tie size, 2, because I have 1 from each end, subtracting all of this bar diameters, and then at the end divide by 2. Why do I divide by 2? Because I have 2 spaces. I have 1 space from here to there. I may mark it. It's going to be from here to there. Another clear spacing between the rebars is going to be from here to there.
Professor, we
Yes.
have 1.5 inch of cover. Is that just because the problem gave it to us, or is that
Yeah,
standard?
it is provided.
Or
But
is
generally
that
speaking, yes, it's kind of a standard.
okay?
Yes, for columns. Yes. So the clear spacing I've just determined here turned to be 4.4 inches. Now this is less than 6 inches. Great. So this column is good. This is a good column. So here's the stuff I checked. I checked the vertical reinforcement ratio. I checked the clear spacing between vertical rebars. Also, I checked the spacing between ties, provided this is not constructed in California. Also, I was able to find out VPN. VPN is the concrete strength of this column. So I completed this problem. Now, any questions?
Can you repeat on previous slide the one you talk about the eccentricity? It's a concentric column. We don't need to mention because it's not mentioned. Moment is not mentioned.
Okay, so let me put it here. I'm going to say, have you seen here any moment? Any indication of a moment?
No.
Yes?
No.
I'm going to say no. Eccentricity. Any eccentricity? No. There's nothing here about eccentricity, right?
Mhm.
So what should I do? I'm just going to say here, you need to determine VPN. Any consideration for any moment? You can say no, no moment at all. Just do VPN for short column. You can say this is going to be VPN for short column. Do you have an equation for it? You can say, yeah, here's the equation, this equation here. So, okay, I need to understand the details of this equation. You can say this is simple. This is going to be the concrete strength on the column. It's going to be the steel strength. You're going to say, what is this phi factor? Say the phi factor, the famous strength reduction factor, right? 0.65 for tight columns. So someone's going to ask and say, what is this 0.8 is doing here for you? Why would you use it? Why would the code put this 0.8 for us? You can say this here to account for small. It's interesting. This is the reason that we have it, which means code says, if you like to go ahead and use this equation, this would be fine. And we're going to allow a little bit of eccentricity. We don't want to take this 0.8 out of this equation because we know that usually you're going to have a little bit of eccentricity, whether you decide on this or you did not decide. So generally speaking, in concrete construction, you should expect a little bit of eccentricity. And of course, there is a check. So right now, we're not going to do any of these checks for the eccentricity. So what I'm trying to say, if you do an eccentricity check, and I'm going to show you later on how this can get done, and you find out that you went beyond the small eccentricity limit, it means this equation here is not enough. You need to consider the additional moment coming from the loading on the column. But for now, we just assume that we have a small eccentricity and nothing that you need to worry about. Are you good?
Yes, thank you.
No problem. All right. Says, okay, this column is good. How about this example here? It says that you have 24-inch by 24-inch concrete column with the strength of the concrete is going to be 5,000. Determine the minimum and maximum column axial load capacities. So, okay, now all of a sudden I hear the new term. It says minimum and maximum. I understand that the column size right here. I know that I have 8 rebars, right? There is no checks here on the vertical rebar or the ties. Ties also is not provided to me. I don't have the ties. All what I have, concrete column size, strength, no moment, which means I'm going to treat this as a small eccentricity, right? And I don't have the vertical reinforcement, but it says minimum and maximum. So I'm concerned here about what does mean by minimum, what does mean by maximum. I don't recall that I have seen this minimum and maximum capacity. Capacity means VPN by Y minimum and maximum, and no reinforcement. Can I go back here a few slides and say, what is that? It says minimum reinforcement provided in the concrete column should have been what? Is 1%. So it's going to be the minimum. How about 8%? It's going to be the maximum. So generally speaking, when you are working on design of a building, and let me now move forward to our example, the column size is going to be kind of determined with discussion with the architect and other trades in the project. Now you know that your column size is going to be 24-inch by 24-inch. For this column here, since the size is known, you need to figure out the range for the strength. How many kips do you think this column is going to be able to support? If you consider the two extremes, the lowest amount of vertical steel ratio versus the maximum amount of vertical steel ratio. So let me throw here some numbers. Let's say I'm working on this column, and I have different columns in the project with different loads. So someone need here to say, with this column size and this strength, what's going to be the range for the axial load? So someone's going to say maybe between 1,000 and 2,000 kips. You say, this is great. Let me look here at the column demand I just calculated out in my analysis. I'm going to be doing here structure analysis, figuring out the column axial load, and then say, yeah, all the column loads that I am looking here at in this project, it's maybe about 1,300 kips, 1,400 kips, 1,500 kips. You see, this is good. It means this column is good to support these loads. And what I need to do now is to work on the amount of reinforcement for each column type. I said, okay, so first thing that you need to do is to figure out the range for the strength. If you are going to put very limited amount of reinforcement, which means 1%, versus 8% for the maximum. Are we good about this definition or understanding? Are we good or no?
One quick question
Yes.
is this related to what we just wrote about the, I have the note right here, the amount for the small eccentricity?
All of them is going to be for a small eccentricity.
Okay, and
because there is no moment here.
Okay, roger that. Thank you.
Okay, no problem. So, okay, maximum versus minimum. So maximum is going to go with the AS max. What is AS max? I'm going to say 8%. What is AS minimum? 1%. So, okay, What is the cross section area? Is right here, the size of the column, 24 by 24. How much is the maximum steel that you can put in there? I'm going to say here's the maximum steel. Take 8% of that. It says 46 square inches. Wow, this is a lot. How can I place them in there? Now, at this point, you don't have the experience, but you know it's going to be a multiple of this 8. But also, you need to know that this number, right? When you lay out the reinforcement, don't forget that you're going to have this symmetry about both of these axes, which means your number of rebars got to be 4 or 8 or 12 or 16. How about 18? Can I put 18 rebars in this column? $18 is okay?
No.
I want to say no. It would be kind of overkill on this.
No, you cannot put 18 rebars.
Any?
How would you put them? Because no, the problem is you need to have symmetry, which means the amount of rebars that you put in each quarter here needs to be the same. So you should be able here to divide safely. You divide here by 4 with no fraction. So 16 is okay, 24 is okay. I'm just talking here about without thinking about the column size yet. So how about 24? 24 is good. 36 is good. How about 30? 30. Is 30 is gonna be okay? Can you put here 30 rebars in this column? Yes or no?
No.
See, no, you cannot. Maybe 32, maybe 36, you should be able to. How about the layout of the rebars? Does it mean that each rebar is gonna be away from the other rebar? Can I bundle them? Can I put them next to each other like this? I say yes, you can do something like this. So if you like, you can put some rebars like this. Okay? Also, you can do this. You can bundle the bars like this. Put them next to each other. Also, you can do this. So you can here 3 and 3 and 3 and 3, and here maybe you can put 2. You know, you can put them in different layouts if you like. You can propose some layouts, or you can just look it up. Usually when you work in an engineering firm, you have previous project that you can just look it up. What is the best way of putting them, right? So you're gonna have here 3, and here also is gonna be 3 and 3 and 3. So you have here 12, and then you have 2 times 4, and then you have 8. Maybe you can put 20. Yeah, can you put 20? Well, think about this. So I said, okay, I'm gonna go here to the largest rebar size, number 11 rebar. This is gonna be the largest rebar size, right? That I can use. I'm gonna use here 28. There's a way to put here 28, but it's gonna be really congested, right? You're gonna have just lots of rebar.
Wouldn't it just be better to increase the rebar size?
Yeah, this is what I did. I went to the maximum rebar size to reduce the amount of rebars. So I said, well, let me try here 28, number 11. How much is AS in this case? You say 28 times 1.56 is going to be 43 inches. So actually, this is going to be the amount of rebars for the cross-section area of the steel that I can use. So someone's going to say, why didn't you use 46? Because I'm going to say here, 46 is impossible. You cannot put them there. You need to think about a good number of rebars that you can fit in the column. So I decided here to go with 28, number 11. And here's AS for it, or AST if you like. Okay, now let me run my equation. Here's the phi factor, the 0.65, right? So this here is going to be my phi factor. This gave the 0.8 for a small eccentricity factor. Here's the concrete strength. And this is going to be the steel strength. How about the steel strength first? I'm going to do it because it's just simpler. It's going to be 43 inches, 0.68 times 60 F sub Y. So done with this. How about the concrete? I'm going to say concrete is going to be the net cross-section area of the concrete. It's going to be equal to A sub G, the 576, subtracting the 43, not the 46. 46 was just a number for the limit that you cannot go beyond. But does it mean that this is going to be your choice and this is the number that you need to use in your analysis? Net 576, subtracting 43 in fraction, and at the end, this is going to be the maximum concrete strength that you can use for this column. It's going to be 2500. So okay, 2500 roughly is going to be the maximum strength they can use. How about the minimum? I said the minimum is going to be here 1%. 1% of the 576 is going to be 5.76 square inches. I'm going to go here with number 8, and I'd like to use number 8. This is going to be a good number to use, 8 rebars at least, because the column size, I cannot really use only 4. I need to use maybe 8. So I said, okay, let me use here number 8. It's going to be 6.32 square inches. Is it okay to use number 7? I'd like you to check with you guys. Is it okay to use number 7? S is equal to how much for number 7?
No, we can't because it's going
Why?
to be on that.
Equals to how much?
6.
Not good. So I really need to go with number 8. So I decided here to go with number 8, slightly higher than this, which is good. Repeat the same equation for this minimum steel ratio that I provided. Now, what is the minimum steel ratio I need to use in my equation? Is it the 576 or the 632? I said, you cannot use this. This is just, that was a limit, but this is my choice here. So my column in this case is called 24 by 24 with number 8. And here's the equation for it. Same thing, A gross subtracting the AST plus F sub y times AST. Phi factor 0.8 for the smooth centricity is going to be 1456. How can I summarize this? I'm going to say for this column, the 24 by 24 was 5,000 KSI. Where did I get this from? Oh, that was given. 5,000 KSI concrete. 5,000 PSI concrete, excuse me. You have a range here for the capacity. It goes from roughly 1,500 to 2,500 kips. Now look at the columns in your project and see how much axial load demand that you have on all of these columns. If the axial load demand is going to be within these two numbers, you're good. If not, you cannot make the column work. Any questions? I'm done with the slide set. I'd like to hear any questions from you guys before I move forward.
Professor, could you go back to the previous problem where you were talking about the clear spacing?
Yeah.
So what is that like? What's that distance from when you solved for the 4.4?
For the spacing, which one? This one?
No, the next one.
Or this one?
Yeah, so what's that 4.4 like in the picture?
This one.
Yeah.
What is the 4.4? Okay. 4.4 is going to be this red line, the length of this red line, the clear spacing. This clear spacing is going to be equal to 4.4 inches. Your max is 6 inches. Let me take you back to the previous slide. Here it is. You see, this is going to be the clear spacing, right? It should be less than 6 inches.
Thank you.
No problem. More questions on this example or the last example? Any questions? Because I need to ask a few questions here.
I have a question.
Yes.
So if you go back a couple slides where we had a picture of all the columns, there's one that's like 10 bars. The spacing, you would divide that, instead of 2, you would divide it by 3 or 4.
This one here? This one?
Yeah, so like, oh, either
The
one
10
of those,
bar,
like, no,
the 10 bar
yeah,
one.
that's the 10
Okay.
bars.
All right.
To find
The
the
10
clear spacing, would you divide that equation by 3?
Yes, but also number of bars is gave before. It is very simple geometry issue that you can just do it on your own.
Cool, makes sense.
Right? So, all right. Now, can I start to ask some questions? Or no? Is anyone ready here for?
Excuse me.
Yeah.
If we have different number of vertical rebars in 2 directions, what's going to be the minimum spacing?
I didn't get that. What do you mean?
Go back to that slide with 10 rebars vertical.
Okay.
So on that 10 bars, if we go to a y direction, we have 3.
Yes.
So 2 spaces, but
Yes.
in each direction we have 3 spaces. So
Yeah, but it depends. Both of them. For any direction, you cannot be more than 6 inches. This is what the code says. So let's say that these 3 bars, these 4 rebars, they are not on equal spaces, right? Like the picture here. You see here the picture, it doesn't show that this distance is the same as this distance, right?
yes.
So in this case, you look at the largest value here and the largest value here, and you confirm that it needs to be within 6 inches. So in some cases, this distance here is 5 inches and this 6 inch, you should be fine.
But when you actually calculate or compute the space on that previous example, you assume that spacing is the same. So right now,
It is up to you. It depends on the design. In our example, they are equal. When you have a system like this, like 8 bars, usually it's going to be equal. Like in this example. This is example you're talking about, right?
Yes.
Because this has to be in the middle. And then you have a bar here at each corner, right?
Yes.
So in this case here, they are equal. You cannot change this fact that they are equal. Right? They're equal. It has to be equal. But in this case, they don't really have to be equal. You can change the location of this 3 bar. So for example, in this direction, this 2 clear spacing has to be equal because this needs to be in the middle. But in this direction here, I can change this. I can go as 5 inches, 4 inches, 4 inches, if you really want to. I don't see a need for this, but if you want to, you can do it this way as a designer.
So, but initially we don't know the spacing in that direction.
Initially, you put this rebar layout and then you do your calculation, your analysis, and then you do a check. If you find it to be more than 6 inches, it means that maybe you need to add the rebar in this side.
So we have to pick something and then go.
Yeah. So for example, I'm doing some analysis here. I did the calculation for this. I found out the clear space between these 2 rebars is 7 inches. What should I do? Let's give you the solution to this. Yes, the solution is to add 1 more rebar in this side. So I'm going to go here with 4 rebars here, 4 rebars here, right?
Yes.
So once you add another rebar, you're going to be cutting the distance from here to there from 7 inches, let's say to 4 inches. And now you have it solved. Okay?
Okay.
All right. Now, can I ask some questions? Are you guys ready? Yes or no?
Yes.
All right, great. Any questions takers? Anyone would like to be asked? Let me write names here.
Sure, let's give it a shot.
Okay, who's the first one? Alex?
Yeah, I'll give it a shot.
Okay, all right, Alex. In this analysis that I'm doing here, right? Did I do California check? Like this California requirement check?
No, you didn't. This was a
Why?
general. Because for California check, you would need to account for 6 inches apart because of seismic codes.
Yeah, but this is the gravity column. Why is the seismic codes getting involved in this?
What was that? I didn't get to hear that
I
clearly.
mean, this is a seismic requirement, but this is here a gravity column. Why do you think a seismic requirement is needed when you have a gravity column?
I would have to say from the notes that I have here, it's
Yeah.
to combat the eccentricity.
Okay, let me repeat the question. You understand that this 6 inches because seismic requirement, like for earthquake loading, right?
Yes.
But this column here is not supporting any earthquake loading, right?
Mm-hmm.
It does not. So why do I care about it? Why would I do seismic requirement in non-seismic member? And why do I think that this question is important here to me? Or to you?
Is it just because we're trying to provide the confinement? No. That's...
Anyone else?
First of all, it doesn't mention in the problem itself that it's constructed in California, so we didn't need to check for that criteria.
This is correct. But
so-
I'm saying, generally speaking, this code requirement, why it is important for gravity columns. What is gravity columns? Non-seismic columns.
Because in California, because of the zoning of that seismic thing, most of the time lateral, if you analyze the lateral forces, then seismic going to govern for the lateral force system. So in that case, the earthquake effect is going to be taken into picture when we do the gravity also.
Is it because it's going to be magnified if we don't? The lateral movements of the earthquake?
Okay. For both of you, I'm going to give you a very good grade for answering, but let me tell you the reason again. Because it is true that this column, they are not designed to support any seismic forces like earthquake forces, but they ride with the building. When the building moves right and left, right, the top and the bottom of the column is kind of set away from each other. So let's say a column was right here at the beginning, right? All of a sudden you do the column like this. So actually you apply some moment on the column. So it is true that the column is non-seismic, but still exposed to lateral drift. This is a term I use, drift, which means lateral movement. And this lateral movement is causing lots of moment and strains on the gravity column. It's actually all columns, not just the seismic column. Are you guys okay with this answer? Make sense or no?
So the reason why is because of, I'm kind of thinking of like an oscillation. Like if the ground is moving and the top, it takes a little bit longer for the, I guess like the lateral movement to reach the top, correct?
Well, the top movement is going to happen for the building for all members, all columns, for seismic and non-seismic, for gravity and seismic members. And this is the reason that we need to consider also some seismic requirements on the non-seismic columns, because you move it. You move this non-seismic columns, you strain it, you drift it, if this makes sense to you. Because it is true that it is not designed to support these lateral forces, but they're exposed to lateral drift.
Roger that.
Okay, very good. I have more questions. Do we have any question takers beside Alex and beside Ramin?
I want to try.
Who's this? Yang Quen, all right. Okay. In this equation here, right? There is a factor for the small eccentricity. Where is this factor? Yang Quen.
0.8. Oh, no. 0.8, yes.
The 0.8. Okay, good. Also, Can you tell me the reason that in this equation here, I didn't use 5.76 for the minimum reinforcement?
Because 5.76 is just the minimum requirement, but
Yes.
we use number 8, so the area of steel is 6.32. So we use this.
Thank you very much. Thank you. That was great. Thank you. I guess this is enough for today for chatting with you guys. I'm gonna move here to the next slide set. You guys have it already online?
Yes.
All right, so what happened here? Now we're gonna be working with spiral columns. Let's see what is the big difference in analysis and design of a spiral column. Okay. Oh, the same slide. Nice. Here's the spiral column that we're going to be working on now. And as you see here for the spiral, you have lots of confinement. You remember this term, confinement? Yes? You're going to see it. You're going to see it. Okay. So here's the amount of confinement reinforcement. You have lots of this spiral. And this is the reason that the performance of the column is going to be much stronger, right? And more ductile than tight columns. Let's look here what happens to concrete properties. Can I zoom in to this? You can say, okay, here I have on this y-axis, I have the strength of the concrete. On the x-axis, I'm gonna have here the strain. Code says that concrete is gonna be failing once the concrete is gonna be reaching a strain of 0.003, right? We understand that. If you bring a sample here of unconfined concrete, performance is gonna look like that. And this number here is gonna be F prime C, the concrete strength, maximum concrete strength. So in reality, concrete is not failing at 0.03, it fails at 0.04 roughly. Of course, it depends on the concrete mix design, amount of cement, size of the aggregate, amount of water to cement ratio that you put in there, lots of variables. But my understanding, usually concrete is gonna be going to higher strains without failure. But according to the code, we're just gonna stop our analysis at 0.03. And you guys, you have seen this. In the analysis for rectangular section, usually we say concrete is gonna be failing at 0.03. You guys remember this value? Maximum strain is gonna be how much? Yes or not really?
Yes.
Okay. Yep. Here's a simple slide. We say concrete is gonna be failing at 0.03. So for the sake of analysis, we say concrete is gonna be failing at this value. So okay, good. So for unconfined concrete, this is if you do here testing in the lab, right? Now, once you provide some confinement, a certain amount, the performance of the concrete is gonna look like this. Look what happened. It didn't fail at 0.04. It fails at more than 0.009. How many times compared to 0.03? I'm gonna say this is gonna be 3 times. Which means the analysis I have done for the concrete, right? Which is this analysis here. I could have gone to 0.009 easily if I can prove that I have good confinement properties. You say, but not in the code. Code says still stop at 0.03. But we know the confinement is gonna bring the strength a lot higher. Look at the strength, you're gonna have also a pump in the strength. But that is not critical, maybe 10% more, maybe 20%. But look at the strain, big difference in the strain when you compare it to the stress change. So the amount of the strength enhancement is completely different from the amount of the strain. So actually putting this confinement reinforcement and providing all of this confinement is gonna help the concrete, especially in earthquake movements. This is where the strain is gonna get very high. But when it comes to the strength, I'm gonna say it's not that critical. But you have some enhancement in the concrete strength. So in your equation here, when you say 0.85 F prime C here is going to be larger. And look at the symbol that I use here. F prime CC, which means confined concrete. And the strain, ultimate strain, here I called it epsilon sub Cu. Here's going to be epsilon sub CCU, confined concrete, ultimate strain. So this slide here, and this analysis is only done in research. So when you go here, if you like to use the HCI code, you don't really do this, confined concrete. And instead, you just keep it at 0.03. But you need to know what's happening here behind the scenes. Behind the scene here, the strength and the strain of the concrete is going to get magnified. You understand that? But the code here allows you to use only 0.03. Now the question is, when I have this spiral column, how would the code recognize this issue of the confined concrete? Because now I have more confined than what I have here in tight column. Say, code is doing well on this issue here. Let me show the equation, what's going to happen. Number one, the phi factor. And instead of using 0.65, we're going to increase it to 0.75. So you have here higher factor when it comes to the phi factor, the trends modification factor. So I'm going to have here higher value. 0.65 to 0.75, you have increase here of at least maybe 15%. I said, okay, is this the only thing? I'm going to say no. Look at the equation. This could be the equation phi PN for the spiral column. So the phi factor now becomes 0.75. But what else? The small eccentricity factor, how come? Now, they changed that from 0.8 to 0.85, right? You guys agree? We have also some increase. So we increased here this factor from 0.8 in tight column to 0.85. So if I'd like here to compare two columns, one of them is going to be spiral column, the other one is going to be tight column. Let me try this quick. You can see here, I have here two columns. Here's a tight column, and this is going to be the spiral. How much is the phi factor in tight columns? Someone help me out.
0.65.
How about for a spiral column?
0.75.
0.75. So, okay, good. How about this small eccentricity?
0.8.
Tight column, it was 0.8, and for a spiral column?
0.85.
0.85. Now, which one is going to be stronger, you think, in your analysis? You say, yeah, of course, the spiral. By how many times? Provided that I have the same cross-section area, I have the same reinforcement ratio, like vertical reinforcement is going to be the same, right? And the cross-section area, I'm going to match it. So both columns going to have the same size and the same reinforcement. What is the ratio? You understand spiral is going to be stronger by how much? You're going to multiply this factor times this factor, right? Repeat the same thing here and then find out the ratio. 22%. Let's say about roughly 23%. The guys agree to this quick analysis? Yes? Or no? Not clear.
Yes.
So again, so what does it mean by this? It means if I have two columns, one of them is going to be a tight column, the other one is going to be spiral column. And they have the same cross-section area. I just matched it. Someone's going to say, it is tough because it's going to be a round column, it's going to be a rectangular column, or a square column. I understand that, but I'll just play here with the size so that concrete is going to be the same. Concrete cross-section area is going to be the same. Concrete strength also is going to be the same. I'm going to pick the same concrete strength. Amount of vertical steel is going to be the same. I'm going to say, here's, I have 8 number 8, here I have 8 number 8. Steel grade is going to be the same. You're going to say the spiral is going to be stronger. By how much? I'm going to say by 23%. This 23% is because the amount of confinement that you put to the concrete column. So it's true the code doesn't say we will allow a strain of this much, 0.009 or 0.008, and they don't say we're going to allow F prime sub CC. They don't say that, but instead they give you here different factors when it comes to spiral column compared to type column to compensate for this issue. So it is good that you understand what is the reason that when we look here at spiral column, we say it's going to be stronger. You're going to say reason is because the amount of confinement that you put in there. Does it sound like a good question for a quiz? Yes or doesn't? Okay, I didn't get an answer. So that's fine. All right, just keep it in mind. How about the steer ratio? This is the same, 1% to 8%. I'm gonna have here a steer range. Fine. Also, I have some limits and some issues here. It says minimum spiral size is gonna be number 3 rebar. So the spiral itself is gonna be number 3 rebar. And the clear spacing between the spiral here is gonna be 3 inches. So you cannot go here more than 3 inches and not less than 1 inch. Wow. Now I understand why I have this 23% difference between the spiral to type column, because the spacing is going to be very small, which means that you're going to have lots of confinement steel around the column. So fine. They say also, if you like to do your analysis here for the steel ratio, for the spiral itself, we're going to give you this equation. Otherwise, you cannot really call it the spiral column, and you cannot use this equation. I'm going to say which equation? I'm going to say this equation. So in order for you to get this 23% additional axial load capacity, you need to do the following. Number one, when you do spiral, it's going to be at least number 3 rebar. The spacing, the clear spacing, cannot go more than 3 inches. So now they confirm that you have lots of confinement. Now they say it's not just about 3 inches or 1 inch. They give you here an equation to figure out the amount of this confinement ratio, or a spiral steer ratio, if you like to call it this way. So you can call it spiral steer ratio or confinement steer ratio. It's okay to use one of these two terminologies. And this steer ratio is actually volumetric steer ratio. Let's see, what does it mean by that? I know steer ratio. What's the steer ratio? You do AS divided by AG. This is going to be the standard steer ratio. I'm going to say, okay, AS divided by AG is called rho. Usually we use rho, right? I'm going to say this is going to be steer ratio. Like when you cut a section, you figure out the total cross-section area of the steel, total cross-section area of the concrete, and then you find the ratio between them. So what does it mean by this volumetric steer ratio? I'm not clear on this. I'm going to say here, look at this. Rho S is going to be equal to the volume of the spiral steer ratio in one turn, which means like one cycle, divided by the volume of the concrete core in that height, the spacing, S. So what is S? S is going to be the distance here from here to there. So I'm going to say from here to there, I'm going to call this S. Let me do it here. This is going to be S. So what is S? It's going to be this distance from here to there. All right? This is going to be S. If you take here the same distance, I'm going to take it here and throw it down. I'm going to put it right here. Right? It's going to be half the way between two spirals. Now, try to cut this. Take a slice of this cone. I'm going to cut it this way and also cut it this way. Okay, take it this way. Find out the volume of this steel rebar. All right, for the tie only, not about the vertical rebars. Divided by this volume that you just cut through. So how much is this volume? How can you do the analysis for this volume? You can say this volume for the concrete is going to be equal to what? It's going to be equal to pi r square of the column, right? Pi r squared multiplied by what? By s. What is s? The spacing. So what is this? This gives you the concrete volume. All right. Are we good about this? So concrete volume is going to be equal to pi r squared. So let me do this. I was going to say R2 times S. So I was going to say, how about the steel volume? You're going to say the steel volume is going to be equal to pi r, which means the length of this tie or this spiral, multiplied by the cross-section area of the spiral rebar itself. Now this ratio here is going to be equal to, what we're going to call it, rho sub s. Where do we have it? It's going to be this one here, rho sub s, volume of the spiral steel ratio in 1/3, divided by volume of the column core and height. Are we good? Said okay, good.
You said that S is equal to 3 inches, but it can also be as minimum as 1 inch, correct?
Yeah, it depends on your analysis. So after you do your analysis. So the question is, where is the core, concrete core? You can see concrete core is going to be this distance from here to there. The concrete contained here within the tie, right? So I'm going to call this is going to be here the concrete core. Okay. And actually this is going to be R. So R is going to be this one here. It's not going to be for the entire column. Because which volume here are you containing or confining with the tie or with the spiral? It's going to be the entire column or it's going to be the core. This area here, this is actually what we call here the core. And the core is going to be the confined volume of the column. This is why we care about this volume here, not about the big volume of the entire column. Let me show you exactly what the code says. S is going to be center to center spacing of the spiral. Yes, I understand that. Center to center spacing of the spiral. A sub G, cross section area of the column in this equation. A sub H, ACH is going to be the cross section area of one core. Which core? You can see for this concrete core here. FYT, of course, is going to be the steel yield point for the spiral. And F prime C is going to be the concrete strength. So I guess I understand this equation. And they have all of these variables. A sub G divided by ACH. You subtract 1, so this is going to be a little bit higher than 1. Multiply by F prime C divided by FYT, and then you multiply by a factor of 0.45. This is going to be your minimum spiral steel ratio.
Could you repeat that one more time? So for the ACH, so that's the cross-sectional area of one core. And are you
Yes.
saying the entire column, or is that just the rebar?
No, this is going to be this one here.
Mm-hmm.
This is going to be the cross-section area of the column
Of
within
the
the spiral.
Within the spiral.
Within the spiral, which means this radius here. Make sense now?
So the two arrows, that would be ACH. Correct?
Yes, this is to determine ACH.
Okay.
Okay. Any questions? Okay. Now also in the code, we have this definition for D sub S. What is D sub S? It's given to the center of the spiral. This is the diameter to the center of the spiral. We have also DCH is given to the outside of the spiral. Now, just to go more into details of this. So how would you do here calculation for rho S? They give you a simple equation. Let's say, look at this equation here. When you do the volume of the spiral, right? You're going to be taking it to ds, because for the length of the spiral is going to be equal to pi times ds, right? Pi d is going to be equal to the perimeter of this circle. You multiply by ASP, the cross-section area of the spiral, divided by the cross-section area of the concrete core, and the concrete core is measured to the outside of the spiral. Someone's going to say, what are you talking about here? If the column size is going to be 18 inch, what is the difference between DS and DCH? Because don't forget, difference is going to be equal to how much? For number 3, it's going to be equal to 3/8 of an inch. Would that make a big difference? I'm going to say no. And actually, we can just assume that DS is going to be the same as DCH for analysis purpose. I mean, this is engineering. We're not doing here math, right? We're not mathematicians.
So Professor, so DS would be the spiral
center?
diameter,
Yes,
right?
the center of the spiral. And
But that would
DCH
be within, let's just say, a number 8 rebar, right? So then DC.
No, this one is going to be number 3 rebar for the spiral.
Oh,
right?
number 3, correct, right?
Yeah.
And then the outside, the DCH would be the same spiral, but with the rebar
From
included.
outside of the spiral. Yes.
Yes.
This is going to be from outside of the spiral. So the difference, if you like to say DCH, if I may write this equation here, subtracting DS is equal to how much? The difference, 0.375, right?
And
It's
that's
very small. It's very small. So there is no, so when you're talking about here, let's say 16 inch or 16.375, how much is the difference? Why don't you just consider DS to be the same as DCH? You can say, fine, yeah, I would do this. So in this case, you cross out pi and pi, right? And get cancel each other, right? And DS can be canceled with one of this DCH squared. So I can cancel one of these. So the steer ratio is going to be equal to ASP, cross-section area of the spiral, divided by what? It's going to be 4 times ASP divided by D divided by S. So it's going to be now much easier, right? So we can simplify this equation, and this is actually what we're going to be doing next time. We're going to be going here in details and see how this is going to get simplified, like what you're looking at. All right. If you like, you can go ahead and sign out, please.